Okay, let's unpack this. We are moving past the lives of individual stars today and zooming out, way out. We're looking at the massive cosmic systems they inhabit, galaxies. Today, we're taking a deep dive into galactic evolution, exploring, well, everything, really, from how the universe built its heavy elements to the shocking, kind of explosive power hidden right at the very center of these colossal structures.
It really is a complete narrative arc, isn't it? Our sources are mapping the entire cycle of cosmic matter, tracking how the universe's chemistry was, rewritten by stars dying, and why galaxies take on the radically different shapes we see, those smooth ellipticals versus the dramatic spirals, and then what the most luminous beacons in the cosmos, the quasars, actually tell us about the high-density, violent youth of the universe itself.
Right. So our mission today is to give you, the listener, a structured understanding of this entire cosmic trajectory. We want to connect the quiet life cycle of a single sun to the explosive history of a billion-star core. We're basically giving you the shortcut to understanding the biggest machines in the observable universe. And, maybe surprisingly, the fact that most of these machines are actually running a deficit. Okay, let's start with that fundamental engine of change, the star. We know that when stars, especially those hitting the red giant phase, reach the end of their lives, well, they shed their outer layers, right? Dispersing that material back into the vast interstellar medium, the ISM. And the star's core then collapses into something dense, hot, a remnant, a white dwarf, neutron star, or black hole.
Yes, and this stellar life cycle is the mechanism for recycling, but here's the critical, maybe counterintuitive takeaway from the sources. If you track the galaxy's development over time, we're not just recycling matter perfectly, we're actually slowly accumulating, you could say, cosmic debt. See, the galaxy hasn't been around long enough for all stars to complete this process. Only the relatively massive stars have finished their path and returned that processed material back to the ISM.
Ah, okay. And this is where the timeline becomes absolutely crucial then. Because stars less massive than our sun, and that's the vast majority of them, they haven't even left the main sequence yet. They're still just burning hydrogen quietly like they always have. And they haven't returned any of the raw material that formed them back into circulation. Not yet.
Exactly. Imagine like a colossal factory that starts with a certain amount of raw material. Every time a product, let's say a massive star, is finished, it leaves some waste. Sure, that can be reused. But the machinery itself, the dead cores, and those really long-lived low-mass stars slowly locks a portion of the original material away, permanently. A really significant portion of matter is continuously sealed off in those dead stellar remnants, white dwarfs, neutron stars, black holes, or it's just held fast in low-mass stars that are going to live for literally trillions of years.
So the fundamental conclusion about the direction of galactic development, it's almost like entropy in this context. The total amount of available interstellar gas, the stuff you make new stars from, in our galaxy, must inevitably decrease as the galaxy ages. We are perpetually, slowly running low on the raw material needed to form new stars.
It's a defining characteristic of an aging galaxy, yeah. But, and this is key, the matter that does get recycled is chemically enriched. It's far more valuable, chemically speaking, than the gas the star started with. Remember, before returning to the ISM, that gas spent millions or billions of years under immense heat and pressure inside the star's core. It's been through thermonuclear reactions.
Right. This is how we move beyond just simple hydrogen and helium. This is where the complexity comes from.
Precisely. Hydrogen burns out, as they say. Helium levels increase. And then heavy elements start to build up inside the star. We see reactions like 3 helium nuclei fusing to form carbon, and then that carbon reacts with more helium to form oxygen and so on, leading to stable isotopes like carbon-13, oxygen-17.
Okay, that explains the basic building blocks like oxygen and carbon, the common stuff. But our sources note we have to account for the really exotic elements, the super heavy ones, even transuranic elements like uranium. You can't just cook those up slowly inside a stable star, can you?
No, you really can't. And that's because the mechanism of gradual buildup, where a nucleus just captures one nucleon at a time, it hits a physical wall, a fundamental limit. It's called the instability barrier. As the nucleus absorbs particles, it quickly becomes an unstable radioactive isotope. And critically, that nucleus decays before it has time to capture the next nucleon. So the slow process of getting heavier just stops. It can't proceed past certain points.
Okay, so if the really heavy stuff can't be made slowly and steadily, it must be made violently,
Yeah.
instantly. This sounds like the moment for the cosmic crucible, the supernova.
Enter the supernova, exactly.
Yeah.
Modern theory points to these cataclysmic explosive events. They provide the necessary environment for what's called the R process. That stands for rapid neutron capture. When a massive star violently collapses and explodes, that's a type 2 supernova, it generates an instantaneous massive burst of neutrons, just a flood of them.
And what does that speed allow? Why is rapid the key?
It allows nuclei to capture 2 or even more neutrons very rapidly before that unstable intermediate nucleus has a chance to decay. It's like firing a machine gun of neutrons into an unstable nucleus. You stabilize it just long enough with one hit to capture the next shot, building it up step by step. And that's how you get stable, heavy elements, including elements far heavier than iron and even the transuranic elements we find on Earth.
Wow. So this rapid-fire assembly line is what gives us the chemistry we need to build planets, rocky planets like ours, and ultimately us. What does this whole process tell us about our galaxy's history, then, in terms of how often these explosions happened?
Well, it tells us the early galaxy was a ridiculously chaotic place, a real fireworks show. These heavy and super heavy elements from type 2 supernovae are constantly mixing into the ISM, enriching it. Now, the rate of massive star formation, which leads to these supernovae, is believed to be proportional to the Q of the ISM density. That's a really strong dependence. So a denser early galaxy meant exponentially more explosions.
A tiny increase in gas density translates to a massive jump in star formation and supernovae, then.
That's the physics at work, yes. Calculations suggest that when the galaxy was less than, say, 1 billion years old, the frequency of these type 2 supernovae was roughly 100 times higher than it is today. So when you total up all that early activity, the accumulated number of supernovae over the entire history of the galaxy is estimated to be around 1 billion.
1 billion cosmic explosions,
Oh.
constantly enriching the medium. That's incredible. Is that continuous enrichment something we can actually verify by looking at stars?
Absolutely. And this continuous enrichment explains a really clear difference we observe between what we call first generation and second generation stars. The oldest stars, the ones formed during the initial galactic collapse, we see them today as subdwarfs or in globular clusters. These are first generation stars. They are very metal poor. Their chemistry reflects the original near pristine composition of the early ISM before it was heavily contaminated by all that supernova ash.
And then there's our star, the sun.
The sun is definitely a second-generation star, maybe even later. It was born after immense chemical processing had already occurred in the galaxy. Its heavy element content, what astronomers call metallicity, is dozens of times higher than these first-generation stars. And that striking difference in composition, which we can measure very precisely using spectroscopy, it finds its natural comprehensive explanation in this whole framework of cosmic recycling and the cumulative effect of, well, a billion enriching explosions.
Okay, so we've established how the matter within the galaxy evolves chemically. Now let's look at the structure itself, because when we look out, we don't just see one type of galaxy, do we? They come in these radically different shapes. The smooth, sort of serene ellipticals, and then the spinning, dramatic spirals.
Right, and this is where we really have to pay homage to Edwin Hubble's foundational work back in the 1920s. His classification system, elliptical E, spiral S, and irregular, was the absolutely essential first step towards understanding the natural laws governing galaxies. It's like Linnaeus classifying life, or the Hertzsprung-Russell diagram classifying stars. You have to classify first. Classification is the necessary precursor to understanding evolution, even if, like the HR diagram, the full evolutionary meaning wasn't clear for decades.
Okay, so let's look at the elliptical galaxies first, the E-types. What defines their structure and their stellar population?
Ellipticals are basically spheroids. They vary in how flattened they appear, from nearly round to quite elongated. Their brightness is highly concentrated toward the center, and their color is often a dead giveaway. They tend to be redder. That's because they're dominated by vast numbers of old, low-mass stars with high hydrogen content still. Very similar, actually, to the ancient spherical halo component of our own Milky Way.
And if they're made of old stars, that strongly suggests their gas supply must be pretty much exhausted, right?
Precisely. Their interstellar gas content is hundreds, even thousands of times less than in spiral galaxies, which means star formation has virtually ceased. It stopped long, long ago. We often call them red and dead galaxies for that reason. They're essentially cosmic retirement homes.
What's fascinating, though, is how their shape is maintained. You might intuitively assume they're flattened because they're spinning incredibly fast. like throwing pizza dough or something.
That's the common misconception, yeah. But when you measure their rotation, the amount of rotation per unit mass is actually quite low compared to spirals. Their observed ellipticity, their flattening, isn't primarily explained by massive centrifugal force pushing the shape outwards. Instead, it's explained by the nature of the stellar movements within them. Their stars move in highly random, often elongated, chaotic orbits. Think of like a swarm of bees buzzing around. It's the collective distribution of those orbits that determines the overall spheroidal shape.
Okay, so contrast that with the spiral galaxies, the S-types, the blue and busy ones like our Milky Way or Andromeda.
Right. S galaxies possess that older spherical component too, usually a central bulge, but they are defined by their flattened gaseous disks, which feature several spiral arms. These arms often have a clumpy, irregular structure within them. And these arms are the cosmic workshops. They contain vast amounts of concentrated gas and dust, and that's where they are continuously giving birth to young, massive, intensely blue, and highly luminous stars. That's why spirals look bluer.
And here, rotation is absolutely the key structural element, unlike in ellipticals.
It absolutely is. S galaxies have a very high measure of axial rotation. They spin fast. The centrifugal force generated by the rapid rotation of the disk and arms is substantial, and it plays a dominant structural role in keeping the disk flat. That rapid rotation is essentially why they remain so flat, and it's also why all the gas hasn't just collapsed into the center long ago.
And we should probably mention the irregular galaxies briefly, too. They're sort of the leftovers.
Kind of. They're characterized by their non-regular shape, often quite chaotic looking. And they tend to be relatively small in mass compared to the giant ellipticals and spirals.
Speaking of mass, the range is just enormous, isn't it?
Yeah.
Our galaxy, the Milky Way, is considered a giant at about 10 solar masses, 100 billion suns worth.
Yeah, and Andromeda, M31, is even bigger, maybe 3 times our mass. But then you have monsters like M87 in the Virgo cluster, potentially 100 times the mass of our galaxy, a true behemoth. Yet at the other end, you have dwarf galaxies as small as 177 solar masses. That's only maybe tens of times more massive than a large globular cluster. The range is vast.
Okay, but here's the major synthesis point from our sources, the one that really challenges the common, maybe intuitive understanding of galactic evolution. We used to think, or it seemed logical, that maybe spirals eventually just ran out of gas, slowed down their star formation, lost their arms, and eventually turned into ellipticals, like an aging process.
Yeah, forget that old idea. Our sources make a very strong case that the differences between E and S galaxies are not primarily the result of evolutionary transformation over billions of years. They're essentially born as one type or the other. Their fundamental structure seems to be predetermined by the initial conditions of the protogalactic gas cloud they formed from, way back near the beginning.
So it's written in their cosmic DNA, so to speak. What were those key determining conditions then?
2 main things seem critical: initial rotation and initial density of the gas cloud. E galaxies, the ellipticals, appear to have formed from denser protogalactic clouds, and crucially, these clouds were characterized by fast, turbulent, chaotic, internal, motionless, organized, large-scale spin compared to spirals. That dense, turbulent state likely caused star formation to happen incredibly quickly, almost in one big burst. It converted nearly all the available gas into stars very rapidly.
And we actually see the smoking gun for this in their environment, where they tend to live.
We do. This formation scenario helps explain why dense, rich galaxy clusters places where the initial gas was likely highly compressed and turbulent due to crowding contain predominantly elliptical galaxies. Everything happened fast and chaotically in those environments.
Okay, and so for spirals, the opposite conditions held true.
Pretty much. For S galaxies, the process seems to have been slower and much more organized. The protogalaxy cloud possessed massive, rapid, organized rotation from the beginning, a lot of angular momentum. That initial rotation was almost like a saving grace. It generated strong centrifugal force that helped prevent all the gas from collapsing immediately into the core and turning into stars all at once. That slower conversion rate allowed a massive, stable gaseous disk to form first, and the gas in that disk continues to settle and form stars much more gradually, even today in the spiral arms. And this nicely explains why poor, more dispersed galaxy clusters, or galaxies out in the field, tend to contain predominantly spiral galaxies. They had the necessary isolation and initial rotation to develop more slowly and form those characteristic disks.
That fundamental structural difference being set so early takes us right back to the ultimate time horizon, the very beginning of the universe. The sources are clear that galaxies formed extremely early in the universe's history. Their age is virtually the same as the universe's age itself.
Yeah, when we look at the farthest objects we can see, the ones with the largest observed redshift, or CE-DIL, historically that record was around 4.5, though recent observations push it even higher, maybe $70 or even $70 or more. Now remember, that redshift still is basically a measure of how much the universe has stretched since the light from that object was emitted. So when light left objects with a redshift of, say, $2.55, the universe's characteristic size was 5 times smaller than it is now, 5 plus z times smaller.
And galaxies must have formed even earlier than the most distant things we can currently see, right? The formation process itself took time.
They almost certainly did. Galaxy formation likely occurred in the epoch between roughly Zilverprox $10 and maybe Zilverprox $100. Now think about what that means for the density. The average density of the entire universe back then was 103.3 to 166.6 times its modern value, 1,000 to 1,000,000 times denser. This incredibly intense high-density youth is where the seeds of all cosmic structure, including galaxies, were planted. We're looking back into the universe's crucible.
Okay, now let's jump from that cosmic history, the big picture, right down to the very heart of the resulting structures. The galactic nucleus, the core. For a long time, maybe most of the 20th century, astronomers just assumed the center of a galaxy was, well, predictable. A simple high-density cluster of stars, just more packed together than elsewhere. Nothing particularly special going on.
That was absolutely the conventional wisdom for decades. It really took the insightful work of scientists like Victor Ambartsumian in the mid-20th century to start emphasizing the non-trivial, unique, and frankly sometimes terrifying properties of galactic nuclei. They realized something important. The average power output of hundreds of millions or even billions of stars should remain incredibly constant over human timescales. It should be smooth. So if you see significant variability, rapid changes in brightness, you have a problem with the simple just stars model. Something else must be going on.
And the evidence for something non-stellar, something active, came precisely from observing that variability.
But the evidence was dramatic and completely unexpected at first. The optical light, and even more so the radio emission, coming from the very centers of some galactic nuclei can change noticeably. Not over centuries, but over periods of months or even weeks. The sheer speed of this change is the critical clue.
Why does rapid change imply a small physical size for the source?
Well, think about the speed of light limit. Nothing can travel faster than light, right? So if an object takes, say, a week to dramatically brighten or dim across its entire emitting region, it means that the region responsible for that energy emission cannot be physically larger than a light week across, about the size of our solar system. If it were significantly larger, the light change from the far side would take much longer to reach us than the light from the near side. That time delay would smear out the observed variability, making it appear much slower and smoother. So this rapid change is essentially proof that a colossal amount of energy, hundreds of times greater than a single supernova explosion, is being released from a volume that is negligibly small by astronomical standards. And this phenomenon is what we call activity. Capital A.
Okay, so we found a cosmic engine that is both incredibly powerful and astonishingly tiny. We know this activity seems explosive in nature, but is it constant or does it come and go?
It definitely appears to be cyclical. Observations strongly suggest that the overwhelming majority of galactic nuclei, including the one in our own Milky Way, are currently quiet, relatively speaking. But this quiescence is likely temporary. Think of it like a terrestrial volcano between eruptions. It looks dormant, but it's not dead. This quiet phase seems to be followed by brief but intense active periods. These might last for thousands or perhaps tens of thousands of years. The underlying physical process seems to be explosive and, crucially, repeating.
And the most dramatic manifestations of this activity, the ones that really stand out, are the so-called radio galaxies.
Yes, the classic example being Cygnus A, which was one of the first strong cosmic radio sources discovered back in 1946. Radio galaxies can have a radioluminosity, the amount of energy they emit as radio waves, that is tens or even hundreds of thousands of times greater than normal galaxies like the Milky Way. Just enormous radio power. Now we know that all this radio emission, whether weak or strong, is caused by the same basic process. Vast amounts of cosmic rays, highly energetic relativistic particles, electrons mostly moving through magnetic fields. It's synchrotron radiation.
Right. And in a normal galaxy, like ours, those cosmic rays are primarily generated by the expanding shock waves from supernova remnants.
Exactly. But in these extreme radio galaxies, that source is nowhere near sufficient to explain the observed power. You'd need an impossible number of supernovae. The sheer magnitude of the radio energy requires the cosmic rays to be generated by much, much more powerful explosive processes happening directly in the highly active core itself. The nucleus is the engine.
And incredibly, we can actually see the relics of these cyclic eruptions in some cases, which provides stunning visual evidence for the repeating nature.
Yes, some radio images provide a beautiful demonstration of this. Typically, these relativistic particles are ejected from the nucleus not spherically, but in two giant opposing jets. These jets inflate huge lobes or clouds of radio-emitting plasma far outside the visible galaxy. Astronomers have observed cases where you see two large, diffuse, kind of faint old radio clouds, clearly the remnants of a previous eruption that happened long ago. And simultaneously, you see two small, bright, compact, young radio structures right near the core, indicating a new ejection event is currently underway. That tells us directly. The engine is firing now, but it has definitely fired before. It visually confirms the repeating cyclical nature of the core activity.
Okay, moving along this continuum of nuclear power, we come to another class of object, Seyfert galaxies. What's their place in this sequence?
Seyferts represent about maybe 1% of all spiral galaxies, so they're relatively rare but not vanishingly so. Outwardly, they look like normal spiral galaxies. They have the disk, the arms, the bulge, but their nuclei are intensely bright and extremely active, much brighter than a normal spiral's core. And their spectra, the light spread out by wavelength, are absolutely critical for understanding them. They show broad emission lines indicating dense clouds of extremely hot gas moving chaotically at enormous speeds, thousands of kilometers per second within the nucleus. This is direct evidence of powerful gas flows, likely jets or winds, being ejected violently from the very central region.
And the overall spectrum itself, the continuous light, also reveals a lot about the nature of the energy production, doesn't it?
It does, yeah. The light signature from a Seyfert nucleus is variable, like the radio galaxies, and it has a strong continuous component, often outshining all the stars in the galaxy combined, at least in the core. This continuous spectrum looks very similar, in fact, to the optical synchrotron emission we see from the Crab Nebulous supernova remnant, which confirms that powerful cosmic ray generation, particle acceleration, is occurring right there in the Seyfert nucleus. So Seyferts appear to be a recurring active stage in the normal development of ordinary spiral galaxies.
Which implies it's highly probable that the nucleus of our own Milky Way galaxy actually went through a Seyfert phase millions of years ago, maybe many times. That's quite a thought. And this brings us to a point we really need to integrate here. The potential impact of all this intense core activity on the possibility of life developing in a galaxy.
Yes, this is a profound astrobiological concern that comes out of studying these active nuclei. When a galactic core is highly active, like in a Seyfert or especially a quasar phase, it means massive amounts of high-energy particles and hard radiation X-rays, gamma rays are being produced and blasted outwards. Now, if these explosions are extremely powerful and happen very frequently, say every few tens of millions of years, which is short on cosmic timescales, the resulting high levels of hard radiation could potentially sterilize large swaths of the galaxy, particularly the inner regions. It could effectively preclude the development or survival of complex life.
So being too close to a frequently or violently active galactic nucleus is essentially a cosmic hazard warning, a keep-out zone.
It certainly could be. However, our sources do offer a fascinating counterpoint, a bit of nuance. It's possible that non-catastrophic levels of such radiation, maybe from less intense or less frequent activity, could potentially be a beneficial factor for life's emergence and early development, perhaps providing an energy source for complex chemical reactions, or maybe driving mutation rates in a way that spurs evolution, possibly even more effectively than the more localized threat or benefit of a nearby supernova burst. It's speculative, of course. But for us, here on Earth, the good news seems to be that observations suggest the explosive events in our galaxy's past were always relatively insignificant on the grand scale. They probably never seriously impacted the overall development of life here. We seem to be in a relatively quiet galaxy, thankfully.
Okay, speaking of significant explosions, that takes us finally to the truly mind-bending objects at the top of the power scale, quasars.
Quasars, quasi-stellar radio sources originally. Or just quasi-stellar objects now. They were first really understood in 1963 thanks to Martin Schmidt. Astronomers had found these objects that look like faint blue stars in photographic plates, but they were also sources of strong radio waves, which normal stars aren't.
Yeah.
Schmidt took a spectrum of one of the brightest, 3C273, and found familiar spectral lines, hydrogen lines, oxygen, magnesium, but they were shifted to much longer wavelength, enormously redshifted. The first one, 3C273, had a redshift Xeris of 0.158 cents, and soon after 3C48 was found at Xeris and 366. Later, they found them up to 744 I-76 and beyond.
And if we apply the standard cosmological interpretation that this redshift is caused by the expansion of the universe, the Doppler effect on a cosmic scale, the sheer magnitude of that shift meant these objects couldn't possibly be stars within our own galaxy.
Exactly. They had to be vastly, almost impossibly, farther away than even the most distant galaxies known at the time. Their huge redshifts place them at cosmological distances, billions of light years away. They essentially define the edge of the observable universe back then, and the implication was simply staggering. To be visible at all at those immense distances, their intrinsic luminosity, their actual power output must be incredible. Many dozens, even hundreds or thousands of times greater than the entire light output of the largest giant galaxies like M87. They are by far the most powerful, continuously radiating objects in the cosmos.
Okay, so this is the absolute peak of the galactic activity continuum. But here's the essential paradox, the thing that makes them so profoundly mysterious, the most mind-blowing fact about them: the constraint on their physical size.
This is what truly makes the quasar such a fundamental puzzle. We established earlier that rapid variability implies small size, right? Well, just like Seyfert's in some radio galaxies, a quasar's brightness also changes noticeably, and not just over months, but sometimes over weeks or even days. This means, absolutely definitively, that the entire region responsible for emitting the energy of maybe 100 giant galaxies cannot exceed a few light weeks or light days in linear size. We're talking about a region maybe comparable in size to our solar system, perhaps 1100th of a parsec, or even smaller.
Okay, let me just restate that because it's so counterintuitive. We have a volume that is negligibly small by astronomical standards, maybe the size of our solar system, out to the orbit of Pluto, radiating hundreds or thousands of times more energy than an entire giant galaxy spanning thousands of parsecs across. That just seems to violate every principle we have about star formation and energy density. How can this possibly be? What could generate that much power in such a tiny space?
This extreme energy density problem is precisely why the search for the quasar power source became one of the central driving problems in astrophysics for decades in the late 20th century. We now understand, as you said, that there's this continuous sequence. Normal galactic nuclei, Seyfert nuclei, right-haro radio galaxies, right-haro quasars. They are all likely manifestations of the same fundamental physical mechanism, just operating at vastly different scales of power output and involving different amounts of mass.
And that mechanism, the leading hypothesis, indeed the only one that seems capable of explaining it, is the supermassive black hole hypothesis.
It really is the only viable solution currently on the table that can explain how you generate that required energy density within that incredibly tiny volume. The core idea is at the very center of these active galaxies, and likely most massive galaxies, including our own, is hypothesized to contain a single supermassive black hole. Not a stellar mass black hole of a few suns, but one with millions, or in the case of quasars, potentially billions of times the mass of our sun.
Okay, but wait. How does a black hole, which is famous for trapping everything, including light, actually generate all this light and energy we see?
That's a great question. It's not the black hole itself that emits the light. It's the intense process of matter falling into it, called accretion. Interstellar gas and dust from the host galaxy, or sometimes even entire stars that wander too close, fall into the black hole's immense gravitational well. But they don't fall straight in. Because of angular momentum, they spiral inward, forming an incredibly fast-moving, flat, orbiting structure around the black hole called an accretion disk.
And what happens in that disk? Why is it so luminous?
Intense friction and magnetic fields. The material in the disk is orbiting at speeds approaching the speed of light, especially close to the black hole. Different layers rub against each other, generating unimaginable heat through viscosity. We're talking millions of degrees. Gravitational potential energy is converted into kinetic energy and then immediately radiated away extremely efficiently as thermal energy, heat, and light across the entire electromagnetic spectrum, from radio waves to gamma rays. This radiation is so intense it can also drive powerful winds and jets, and it heats the surrounding gas clouds, causing them to move chaotically at those enormous speeds we observe as broad emission lines in the spectra of Seyferts and quasars.
And the variability we see, the flickering and flaring over weeks or days, is that explained by the lumpiness or inconsistency of the material falling onto the disk?
Precisely. The activity, The brightness seems to be tied directly to the irregularity of this gas infall. If a massive clump of gas or a star falls onto the accretion disk, the whole system flares up dramatically. When the gas supply temporarily thins out, the engine dims down. So, quasars are simply systems where the central supermassive black hole is truly enormous, maybe billions of solar masses, and it's currently feasting. It's accreting gas and dust at a monumental, record-breaking rate, powering that incredible luminosity.
And even our own relatively quiet galactic core, the one in the Milky Way, Sagittarius A, it's still a major power source by normal standards, isn't it?
Oh, absolutely. Even our core is active, just not currently in a bright, explosive quasar or Seyfert phase. Its central source, Sagittarius A star, SGRA, which we're now very confident is a 4 million solar mass black hole, is still contained in a region less than a parsec. Across radio observations constrain parts of it to be potentially even smaller than the size of Jupiter's orbit around the Sun. Yet even our quiet core still releases something like 1040 ergs per second of energy, largely in the form of accelerated particles, cosmic rays, and some radiation. Now, to put that in context, that is still about 1 million times the total power output of our entire sun. So that quiet energy is what remains when the supermassive black hole is relatively starved, when it's not being fed a massive supply of gas, it's just simmering.
Before we wrap up the course, we should probably touch on the observational difficulties again. We can't actually see our own galactic core using normal optical telescopes because of all the dust in the way.
That's exactly right, because our sun sits within the galactic plane, relatively close to it. The huge amount of interstellar dust lying between us and the galactic center absorbs almost all visible light. It's like looking through thick smoke. So we rely entirely on observations at longer wavelengths that can penetrate the dust, mainly radio waves and infrared light. And those observations confirm that our core is indeed a compact radio and infrared source, roughly 1 parsec across in its wider influence. It contains millions of stars packed incredibly tightly, making the stellar density there tens of millions of times greater than it is out here near the sun. It's an extreme environment.
But the Andromeda Galaxy, M31, our nearest giant spiral neighbor, is different in terms of viewing it.
Yes, completely different viewing angle. Andromeda's core is fully observable optically, which is a huge advantage for studying it. This is simply a matter of geometry. Its equatorial plane, its disk, is highly tilted relative to our line of sight from Earth. That means we look through a much thinner layer of its own light-absorbing interstellar dust when we look towards its center. This gives us a much clearer optical view of its central bulge and nucleus structure compared to our obscured view of the Milky Way's core. So we've really charted quite a cosmic trajectory today, haven't we? We've moved from the microscopic creation of heavy, even transuranic elements inside supernova blasts, to the macroscopic structural birth of elliptical and spiral galaxies, driven, it seems, by those initial differences in rotation and density. And we concluded by exploring the most grand explosions in the universe, the quasars and active nuclei, which are powered by these incredibly tiny yet unbelievably powerful engines, almost certainly supermassive black holes, hiding at the very centers of their host galaxies.
It really is remarkable how tightly linked the very early history of the universe, the conditions just after the Big Bang, are to the structures and phenomena we see today. Everything from the chemical composition of our planet and ourselves traced back to supernovae, to the fundamental shapes of the galaxies we inhabit, set by those initial conditions.
And that entire picture, though it hangs together remarkably well now, still has its lingering mysteries, its puzzles. One long-standing puzzle, which connects the history of the early universe and the power of these active nuclei, is actually the distribution of quasars in space.
You mean where they're located, not just when they existed?
Just exactly. Quasars, which are the most energetic objects we know, seem to definitively avoid the dense environments of rich galaxy clusters, which is odd because we know that at least 90% of all galaxies reside in those clusters, or groups. So why the most active, most powerful cores prefer to exist in more dispersed, less populated regions of the universe, that remains an important fundamental problem that we haven't fully solved yet. Something for you, our listeners, to maybe mull over as you look up at the night sky and contemplate those distant, powerful beacons,